Now let's go over here and look at sedimentation rates, right? So one of the things we can point out here with sedimentation rates is that when you look at the sea floor, these abyssal plains, right, the flat regions of the ocean, you have about 500 to about, at the most, 600 meters of sediment sitting on top of the basalt. So remember, the basalt is the bulk of it, but then you have the sediment. If the oceans were as old as the continents, you know, remember the continents are up to 4 billion years old in some places. If the oceans were that old, then you should have like 10 kilometers or 10,000 meters of sediment on the seafloor, and yet you don't. So which is, again, evidence that the seafloor is not very old compared to the continents, right? So that's his criteria for the sedimentation rates. Nowhere can you find, at least on the deep abyssal plains, nowhere can you find sediment that's very thick, nowhere near those 10,000 meters, 10 kilometers. And finally, the third criteria was if there is magma injecting, you know, these tension cracks forming here, injecting into the seafloor, causing the seafloor spreading or helping it out here, then earthquake waves, seismic waves that move through rocks, they should slow down here because the rock is soft there, right? In fact, there's magma. And sure enough, when we go and we analyze earthquake waves that travel through mid-oceanic ridges, those seismic waves slow down, which means it's soft rock there, right? So those were his 3 criteria. Now, as we continue on here, we'll look at, again, looking at these magnetometers. So the way these work is, remember, Earth has a magnetic field. The lavas, when they erupt from the mid-oceanic ridge, the magnetic minerals, the magnetite, are acting like little tiny compass needles, and they point in whichever direction Earth's magnetic field is. And then they record the paleomagnetism, the remnant magnetization found in rocks. But one thing that was unusual, when ships started recording the magnetism of the seafloor, they noticed that some parts of the seafloor had positive signatures, just like we have today, but other parts had a completely opposite signature, a reverse signature, which is called a negative anomaly. So it was very strange, is how can huge swaths on the seafloor have signatures that are completely opposite to what we have today? In fact, what this implies, or what this was telling the scientists, is that the seafloor in these areas of negative anomalies formed, or at least their magnetic minerals are pointing to somewhere near the geographic South Pole, which means at some time in the past, the magnetic North Pole must have been somewhere in near the geographic South, which was crazy. That's why they called it an anomaly, right? And people didn't really want to believe it. But what happens is Earth does go through periods of magnetic reversals. Remember, the geographic poles do not change. They're always, North Pole is always going to be North Pole, South Pole is always South Pole. What changes are the magnetic poles. They can completely flip around. And here on the seafloor is the evidence for that. It was very overwhelming. Okay, we'll continue with looking at these magnetic anomalies on the seafloor. And one of the predictions of seafloor spreading is that if the seafloor is forming at these mid-oceanic ridges, the lavas that form there are all collecting the same paleomagnetic signatures at that time of formation. But then they get cut in two. One goes off in one direction, in this case to the left. The other one goes to the right. Remember, they're going directly away, perpendicular to these mid-oceanic ridges. In fact, this mid-oceanic ridge is one that's off in the northwestern United States, off of Washington State and Oregon. There's a Gorda plate down here, Gorda Ridge off of Northern California. But the same idea. And so if we look, so currently all the lavas that have formed in the last about 780,000 years, because that's the last time the reversal occurred, are going to have a normal magnetic anomaly or positive anomaly. So in other words, the magnetic minerals, the magnetite inside the lavas here near the Juan de Fuca Ridge are pointing toward north, just like our field is today. But as soon as you go a little farther off the ridge, you find that there's a region of a negative anomaly. So these magnetic minerals in this swath of the seafloor are actually pointing toward geographic south, opposite direction as today's magnetic field. So that's called a negative anomaly. And we see that anomaly right in here as well. And then you see another positive, another negative, and basically they become mirror images. So the patterns you see on one side of the seafloor from the ridge axis, and the other side are mirror images, and they're telling us that the seafloor, these regions formed here, split in half, and they were moved to their current positions. There's more on this as we go along here. So looking at reversals in Earth's magnetic field are recorded in iron-rich rocks. Remember the mafic rocks, such as basalts. So here's like a volcano on one of the Hawaiian volcanoes, and we want to do this collection on subaerial volcanoes, volcanoes not underwater, volcanoes that are actually under the air, where we can go and sample these, right? We don't have to go to the sea bottom to collect the data. And we find that as we're looking, so this Gilbert period is a reverse polarity, because note that the dipole is reversed here, then it reverses here for the Gauss. There's another big reversal in the Matuyama, and then the Bruns is back to normal. So we're currently in this position here. So this is recording 1, 2, 3 reversals right there, right? And again, we can radiometrically date these lava flows to figure out when these reversals occurred, right? And so looking at this, remember normal polarity, the dipole of the bar magnet, in this case the positive end down here, but it leaves the magnetic south, re-enters magnetic north. Here we flip the dipole around, right? So that's a reversal. And so again, the lines will leave, in this case, magnetic south is up here near the geographic north pole. So that's kind of the thing to understand, is when we get a magnetic reversal, magnetic south is now up near the geographic north, and magnetic north, see, that is down here near the geographic south. So the field flips around, but the geographic poles remain the same. And people ask, well, how does this occur? And you know, it occurs at anywhere from 500,000 years to a little over 1 million years. So it depends. It varies. And some people think we're actually overdue for a reversal. And how does it occur? Well, we know that the liquid outer core, right? It's iron. It's dense. In fact, the density of the core is about 10 to 13 grams per centimeter cube, whereas mantle is only about 3 to 5 grams per centimeter cube, and continental rocks are only 2.7 grams per centimeter cube. So the core is very dense. And because Earth is spinning, this core is spinning. But it's actually because that outer core to mantle interface is a liquid to rock interface, right? Which this is what scientists kind of agree on, is that it seems that there's a slightly different rotational rate for the core than the rest of the planet. And that slight difference over time can yield to these reversals, right? And so that's how we get them. And they happen. And in fact, and like I said earlier, we're overdue for a reversal. Now, this, your book kind of covers this, magnetic reversal chronology. Remember the timing for the last 4 million years. And again, you sample lavas that haven't been weathered by seawater, which are fresh. So you want to do these on land. And we find that the reversals occur at this time here, right? So you can kind of look at this in your textbook here. And then this is just showing how when you get a positive anomaly, you want to have the rock, the seafloor rocks, the basalt, to have the same orientation of their dipole as Earth's current magnetic field, right? If they're different, then that's when you get a negative anomaly, right? So that means, in this case, magnetic north is down here in the southern hemisphere, right? So that's a reversal right there, which would be the negative anomaly. Now, seafloor spreading predicts that magnetic anomalies should be mirror images across the mid-oceanic ridge. So here we're looking at the mid-Atlantic ridge just south of Iceland, and we see that at the ridge axis where lava is erupting, and for the last 780,000 years, we see normal polarity, right, or positive anomalies. If we go to regions that are a little bit older than that, we see a reverse polarity, right? And then even farther, be back to a normal. So this normal matches that normal. And then this reverse one over here matches this reverse one over there. So that's how these anomalies are forming. And remember, the lavas erupt at the ridge axis. They pick up their paleomagnetic signature. It cools below that Curie point, locking in permanent record of paleomagnetism. Then the seafloor splits in two and starts moving away over time. That seafloor that's moving away has a history. It's recorded its signature, paleomagnetism, at the time it formed, right? So in this next picture, we're seeing how these anomalies may form, right? So at time 1 here, magnetic anomaly stripes are created as a mid-oceanic ridge adds new basalt to the spreading oceanic crust. So here the lava erupts, picks up its signature. In fact, here it looks like it's a reverse polarity. Then new lava forces that older lava aside, but now it's normal polarity, right? And then more lava forces that apart, it's back to reverse. So then we get this reverse, normal, reverse, right? So we get that pattern on the seafloor. And that's how these magnetic anomalies, magnetic stripes in the seafloor, that's how they form, right? Through these seafloor spreading process here. And then when we go across the seafloor, note that we should expect to see, again, a mirror image of positive and negative anomalies on one side as the other side. So if you think about this positive anomaly here will match this positive anomaly. Did you hear? This positive one match that positive. This negative one should match this negative one, right? So the seafloor here is the same exact age as the seafloor here. And you can think of this negative anomaly and this negative anomaly as being twins, both born at the mid-oceanic ridge, split in two. One goes off in this direction, the other goes off in that direction, right? And so the other thing your book points out is that the width of the magnetic stripes is proportional to the duration of normal or reverse magnetic field conditions. So that's one thing we should keep in mind. I think there's a question about that in the Smart Work quiz. All right, so let's stop here for now.